Yes, thank you. And I'd like to thank the organizers who have organized an amazing, huge conference that so far has been a real pleasure to attend. After thanking, I should also apologize because I realized that I prepared a lecture that is a rather general audience lecture, and then I look around and I see that half of the people in the room know the subject much better than I do, and so I hope that you'll ask me tough questions, and that way maybe use your questions. We can try to have this a nice talk. It's about duplication, and fittingly, I think some of you have heard me already talk about this this subject. So here's part 2 of the duplication. I brought my own blackboard because I don't like the whiteboards, but somehow I forgot to bring my chalks, so I think I'll have to still digitally write on this blackboard. So let's see if this works. It doesn't. Yeah. All right. So that's my title, and the picture is trying to illustrate what's going on here. Does it? Okay, it seems to work. All right, so I'll start with something that has been mentioned before, the original duplication, and we're celebrating the 100th birthday of this duplication. I'd like to make a certain number of points about this theorem that you all know, but maybe first I'll illustrate it with a picture here, so that we really see what it's talking about. And I think the first point I'd like to make is that this is often presented as a motivation for the notion of amenability, and I'll also follow this track. However, I think this is slightly misleading to present it this way, because in fact, what this is showing us is not so much that there's not some notion of measure defined on the entire three-dimensional space. Nobody in their right mind would try to weigh the whole of three-dimensional space and say that there's something wrong with the mass of the entire three-dimensional space because of this duplication, right? What this is illustrating is that there's something wrong with defining the mass of the ball. And now, if I take the ball and, unlike Hausdorff, I really move it to create two separate balls, I haven't contradicted the amenability of anything. I have just contradicted that there be a mass defined on the whole three-dimensional space, which would be finite and non-zero on some nice particular subset given by the ball. Right? Amenability is a much more restricted thing. Amenability is about having a mass normalized on the entire space or on the entire group. So this contradicts what is called superamenability or supraamenability, and that's what von Neumann has really introduced to study this paradox conceptually. And there's a very special case, amenability, which has been studied much more successfully simply because supraamenability is a bit too difficult to study and amenability is easy, and so we'll just follow the easy track. So that's the small warning about this statement. Now, if anybody in this room hasn't seen that before, then I think it's important to also give the nicer version, the ultimate version given by Banach and Tarski, where you can replace the ball or the two balls by whatever you like. And so, being Swiss, I decided to replace it by the following statue here. So you need to cut the ball now in more than 5 pieces. It's not anymore 5 like for the duplication, but a great number. And you can create this thing, which is, I think for the francophones, it's called tel père, tel fils, this statue. It's somewhere in central Switzerland. All right, so that's the Banach-Tarski paradox. Now let's try to explain this paradox. Okay. So here's how the proof works. And I've heard this explanation before. I think it was yesterday in the lecture by Michael. So that this is all due to the existence of a free group. And the free group is paradoxical. This can be illustrated as follows. So here we see a picture of the free group on 2 generators. And if I can add something to this picture, right? If I can add something to this picture, you see that a small part of the free group looks eerily similar to a much bigger part of the free group. So you see here, if you look at this picture, that 1/4 seems to be the same as 3/4. And if you believe that 1/4 is equal to 3/4, then you certainly believe with some more bookkeeping that 1 is equal to 2. And that's exactly the bookkeeping that Hausdorff has produced. So he has taken such a paradoxical, it's not yet very paradoxical, but it's mildly paradoxical, the fact that 3/4 of the free group look like 1/4, and you can then transport this paradoxicality to anything on which the free group acts just by taking orbits. So that's the graphical explanation. And so what I would like to talk about today is the question of the converse. So I've just this morning I found a nicer converse than the ones that I used to use. And this is really a mathematical converse, as you can see. So the converse question is it true that paradoxes always come from free groups, right? So that has been called somewhat apocryphically the von Neumann problem. So here you see the converse. Is this really the only source of paradoxicality? Now, as I said at the beginning, the room is full of specialists, and so the specialists know that the answer is no, that this is not the only source of paradoxicality. But I'd like to challenge the specialists and tell them, really, so can you show me a paradox without the free group? Because I haven't seen one. So I know that there are theorems and that these theorems have proofs, but I haven't really seen a paradoxical decomposition that's not coming from the free group. And the paradoxical decomposition of the free group, I have seen it. We've all seen it. It's there. Right? So here, I mean, I've only drawn the 1/4 equals 3/4 picture, but you can easily move this around and see that the other branches of this sort of TV antenna here are also identical to the blue one. And so here you really see a paradox. It's completely explicit. You can write it down, and the proof takes only a few lines. In fact, it's one of these classical paradoxes that go back much further. I think that Galileo had already a paradox where he was explaining that it's strange, isn't it, that there are as many even numbers as odd numbers, because you have a nice way to create an even number out of every odd number that is 1 to 1. But then again, there are twice more numbers than even numbers. And I think Galileo was taking as an example integers and squares of integers, maybe not even and odd, but squares. So there are even less squares, but there's an obvious bijection between squares and positive integers. Right? So here we're just doing the same thing. It's a simple notion of infiniteness, and it's perhaps a bit, the tricky part is perhaps to say that, yeah, well, you can decompose a sphere or a ball is even a bit more tricky along orbits of the free group, but that's the paradox you can see. And the other paradoxes, I haven't seen them yet. Right? So in particular, we know that certain things are paradoxical, but that you need to cut them into much more than 4 pieces to see the paradox. So there are recent results that indicates that, in fact, an arbitrarily high number of pieces might be needed, depending on the group you start with, but none of these pieces have been seen explicitly. Right? So that's what I'd like to discuss today, and I will not answer the question. I will not give you a new paradox. I will not be able to. I would like to, but I can't. So perhaps somebody else can do it. All right. Now, the summary so far, I'm constantly looking at my watch, not because I'm nervous, but because it stopped. So when at the border, when I came from Switzerland, at the border, in the train, the watch stops. I can only hope that it will start again when I cross the border again. But so I have to check sometimes the time on. And nobody wants to lend me a watch somehow. 10:25. All right, so it's time for summary. So here's a summary of the situation. The paradox we know comes from the free group. And therefore, it's natural to ask, can you find another form of paradox, or at least are there other paradoxical groups not containing the free group? That's the question I want to ask. And this thing doesn't work. And this justifies the following definitions. So a mean, as Michael defined it yesterday, is a probability measure on a space or on a group, and later in this talk it will be even on a relation. So that's a mean, and the group is called amenable if it carries an invariant mean. All right, so this definition comes from the fact that it's the obvious obstruction to doing this kind of trick, because if I can duplicate something, then the duplicated weight or mass or mean is certainly twice that I started with, and there's an absurdity there. So it's the obvious obstruction. Now, what is deeper is that it's the only obstruction. And I want to insist here that this is a theorem of Tarski that has nothing to do with the free group. So the interesting part, the difficult part, it's not exceedingly difficult, but the difficult part of this theorem is that you need to show that just because you don't have a mass, a notion of mean, that you do have a paradoxical decomposition. And difficulty here is, again, that you're not going to exhibit it. Right? Perhaps this paradoxical decomposition, as we know, perhaps you need 10 to the 10 to the 10 pieces to witness it, and that you cannot construct it with less than 10 to the 10 to the 10 pieces, because you don't have a free group. But it's an existence result. So Tarski proves that these two things are really equivalent, and therefore amenability is really the obstruction to paradoxicality of the entire group. So I mentioned again, and for the last time, that this whole subject is somehow a simplification of the original question, because in the original question, you are not trying to decompose the group of rotations of the sphere, you're trying to decompose the sphere within 3 space, which is a much more interesting question, I think. Right? You could imagine that there are amenable groups that are paradoxical, right? So that have paradoxical pieces. All right, so that's the summary. This thing will never work for me. Maybe if I take it over the border, it will also start again. Okay. So that's the summary, right? Are there any non-amenable groups that do not contain the free subgroup. That's what I want to talk about. In fact, I want to give you complete proofs that they are. And yeah. Okay. That's just name dropping. And the purpose of this name dropping here is to try to convince you that amenability is extremely interesting in all kinds of subjects for reasons completely unrelated to paradoxicality and to amenable groups, because amenability, I claim, is very useful to study non-amenable groups. So for instance, I'll just take maybe one favorite, I'll pick randomly this here. So the second last is a topic that I like a lot. So Grisha Margulis has made incredible advances in the study of arithmetic groups, which are definitely not amenable and they contain free subgroups. How? Because somehow I would say the starting points of his rigidity and arithmeticity theorems is to realize that all these groups, they in fact are connected to something amenable. And there's very precise meaning in this. So let's take your favorite arithmetic group, for instance, n by n matrices over the integers, or over the integers of some number field. That's the typical example of an arithmetic group. It's not at all amenable. Now, it lives naturally in n by n matrices over global fields. For instance, real n by n matrices or periodic n by n matrices. This again is not at all an amenable group. So think of SL2R, SL3R, SL4R. They're not at all. They're less and less amenable, right? However, these groups all contain a co-compact amenable subgroup. The group of upper triangular matrices is soluble. This is amenable. So from the viewpoint, if you're one of these people who thinks that quasi-isometric things are the same thing, then any semi-simple Lie group is quasi-isometric to an amenable group. All these property T groups that are not at all amenable, they have a co-compact amenable subgroup, right? And this fact is extremely useful for proving rigidity results. So that's really one of the starting points. It's not the historical starting point of Margulis. His historical starting point was basically the Osseledet's theorem, but then you can reconceptualize this into using the notion of amenable actions. And so amenability plays this completely fundamental role to prove theorems about these non-amenable groups. Okay, but I would like to now, if I think time permits, it's still 7 a.m., so I think I can now take some time to give you an illustration of another instance where amenability pervades another topic, and that is the geometric case here. So I'm going to take a little bit of time to illustrate just on one slide some old and some more recent results about amenability in the context of geometry. So this is one of my attempts to come a bit closer to this topic of this, to the many topics of this conference, perhaps. So let's try to do that. Okay. So first of all, I'd like you to look at the red equation here. So the red equation suggests that you can take the intersection of non-positive curvature, which is in geometry, with amenability, and that the result should be flat spaces, if you talk about the geometry, or flat groups in the sense of crystallographic groups, so Euclidean crystallographic groups, if you think about the algebra. So what does this really mean? Let's try to make it specific. And I'll start with Avez, who in the 70s proved the following theorem. Suppose you have a closed manifold, a closed Riemannian manifold, that's your space, and your geometric assumption is going to be that it has non-positive curvature. Then you can try to combine the properties of this manifold, the space, with its fundamental group. So the space, we assume it has non-positive curvature. The group, we assume that it's sub-exponential growth, in the words of Avez, and then Gromov and Zimmer have noticed that amenable is really the operative word here. Then Avez proves that this manifold is flat Euclidean. Okay? Very strong, very nice theorem that takes two completely different fields and proves that if you put together non-positive curvature, sectional curvature with amenability or sub-exponential growth, you get flat Euclidean manifolds with Euclidean groups. All right, so the ultimate version of this theorem is due to Adams and Ballman, and is stated in the more general setting of cat-zero spaces. And the conclusion is the same. So I find it even more remarkable, or maybe much more remarkable, this theorem, because you start with a singular space. You start just with a metric space that satisfies one inequality in addition to the triangle inequality. Only one inequality, the cat-zero inequality. It's a simple inequality expressing some sort of combinatorial form of non-positive curvature. And it could be a horrible space. It could be a space with hair growing on it or things like that, and or simplicial, singular or something. And they prove that, in fact, if it is amenable as a group, so if you have a discrete co-compact group of isometries that is amenable, then the space is actually Euclidean, and in particular the group is a Bieber group. Okay? So this is an ultra-general statement. There's only one assumption that is hidden here, and that is the assumption of geodesic completeness. That is a slightly technical geometric assumption, the assumption that any geodesic segment can be continued. And this is to avoid that you grow short stubble on your space, and that would contradict this theorem. Take your favorite crystallographic group, and at every atom of your crystallographic lattice, you grow a short hair. This is still cat-zero. The cat-zero notion of non-positive curvature is general enough to accommodate this, but it's certainly not a purely flat Euclidean space. Okay. So that's the Adams-Ballman theorem. And now I would like you to find a contradiction in what I've said so far. There's something that's not quite right here. Because I tried to make this point that certain things that are not amenable at all have a co-compact amenable subgroup. So, for instance, you take hyperbolic space, Lobachevsky space, for instance, the Lobachevsky plane. This is not at all Euclidean, and yet it has a co-compact group of isometries that is Euclidean, that is amenable, right? The AX plus B group. Now, the point is, the reason it doesn't contradict this theorem here is that when people are talking about cat-zero groups, they have in mind discrete groups with no topology. And so, in particular, you want your action to be properly discontinuous, and that doesn't work in the Lobachevsky example, right? But if you want to bring this to the next generality, you should ask yourself, okay, fine. So, what happens if I allow, as I should, topological groups? Because after all, the isometric group of a nice manifold is in general a locally compact group. So, how about the general non-discrete case? That is, the statement would be, I have a space that's non-positively curved, for instance, a manifold. I think the question is interesting even for a manifold. Then I have an amenable group that acts co-compactly on it. So I have a manifold or space with a co-compact amenable group of isometries. What is the conclusion? And the first thing to notice is that there's no hope for classification of such things because there exist Heinz manifolds. So this is an uncountable family of manifolds that in fact have a structure of Lie group. And these manifolds, so there are uncountably many of them, and they all have an amenable, in fact, a soluble fundamental group, a soluble isometric group, and they're all negatively curved, and so you will not be able to really classify them into something discrete. However, they are very degenerate, these Heinz manifolds, in the sense that they are very non-isotropic, they're very non-symmetric, in the sense that there's a canonical point at infinity that is fixed by all isometries. So these manifolds typically look like warped products. They really look like you have some kind of conical construction where you have one direction that goes to infinity that is a distinguished canonical dimension, and transversely to that you kind of compress your space. So this is a very degenerate sort of example. And we want to rule out this example by saying that the manifold should be at least, or the cat-zero space at least isotropic enough or homogeneous enough that there shouldn't be a favorite fixed point at infinity. All right. So under this setting, together with Pierre-Emmanuel Capras, we finally this year managed to complete a program that we're sweating on for 5 years, I think, or perhaps more. And we managed to classify these things. And so here's the statement. It looks very similar to the Adams-Ballman theorem. But the conclusion has to allow for many more interesting spaces than just the Euclidean spaces. So the statement is, under exactly the same assumptions, if your isometric group is amenable, then you understand completely the geometry of your space. Your space could be a symmetric space. Symmetric spaces are classified. There are countably many of them. There are Euclidean spaces, hyperbolic spaces, and more general things. But they're all given by a semi-simple Lie group. And then there could be Breuer-Titz buildings. These are also classified. So buildings are slightly wild, but Breuer-Titz buildings all come with an algebraic group associated to them. So it's the non-Archimedean version of symmetric spaces. And then there can be trees. More precisely, hemi-regular trees, so Basser trees. They're almost examples of Breuer-Titz buildings. It's just a bit more general because when you have a Breuer-Titz tree, you have some arithmetic restriction on the valency of your tree. And so Basser trees are more general. But so what we prove is that, in fact, if you add together this amenability condition on the group and non-positive curvature on the space, then you can classify completely the space and the group. So the spaces will all come from these algebraic constructions, symmetric spaces or buildings, and the group accordingly will all be algebraic groups, with the exception perhaps of these three groups, right, of these Basser groups. So that's the indiscrete Bieber-Bach theorem, I would like to say. All right, all this was an illustration of how amenability can marry with geometry to produce this kind of large family here. And
what means pair xg?
What means what?
Pair xg.
Ah, okay. Okay, so this means that X is a metric space, which is cat 0. G is a group that acts by isometries co-compactly on X.
Why call this cat 0 group?
By definition. Okay, so historically, I think what was called cat 0 groups historically was a group which admits a cat 0 space on which it acts properly continuously co-compactly. Right? Just like you could define a hyperbolic group by saying it's a group which admits a hyperbolic space on which you act discretely co-compactly. But I think it's a bit more precise to define the cat 0 group not to be a group that admits something, but the pair of the group ends this thing.
So you call it locally compact. What is locally compact?
What is locally compact? Well, X and G.
Both.
Yeah, but the local compactness of one is equivalent to the one of the other. So
the additional edge.
Yeah. So please do interrupt me if there are more questions, because I have no time limit since my watch stopped. But
can you comment on the final line? So commensurate means.
Commensurate. What is? I think it's also an acceptable adjective, isn't it, John? Commensurate as adjective, yeah. So that means basically that up to a compact kernel, it lives as a closed co-compact subgroup. Okay, so I think discrete group people have this notion, and they maybe say that they're commensurable sometimes. Commensurate fits better on the. You see, I reached the margin already. So yeah. Yes.
I must have missed something, because I have the impression that your theorem has a stronger hypothesis and a weaker conclusion than the previous one.
All right. So I think there's a very strong assumption in the first one, and that's the one that is maybe implicit, is that in the first one the group is an abstract group. It's not a topological group. It is what Eve likes to call a discrete group, but it's a group without a topology. So it isn't even discrete. It has no topology. Yeah. All right. So let's go back to the talk itself, if I can. I can't. It's terrible. Okay. So this slide you've seen already. Right? We want to see if groups can be paradoxical without containing a free subgroup. Okay. I would like to have an assistant to turn the pages if it's possible. Okay, so the answer is yes, there are such things. We've known them since the end of the 70s, or maybe in this part of Europe since the beginning of the 80s. And they're sometimes called monsters, but I guess this is more a sign of respect than of actual fear. So the monsters from the 80s, okay, I guess in this country that's what you have in mind if I say that. But, why doesn't this go away? Okay. So monsters are, for instance, Tarski monsters. So one of the things that is so monstrous about them, I guess for Tarski, what's monstrous about them is the subgroup lattice structure. So it is groups whose subgroup lattice is extremely limited. They only have cyclic subgroups. And they're monstrous in at least two other ways. They're monstrous because they're not easy for most people to construct. And they're also monstrous because, and I'd be happy to be corrected if I'm wrong, but I think it's the case that the smallest examples, the example with the smallest cyclic subgroups have still order of the order of 10 to the 75. That's what I've heard. Something like that. So that's big. That's big, right? And these are beautiful counterexamples because for sure they will not have free subgroups. And I guess for group theories, maybe it's not the most interesting thing to know that they're non-amenable. What's really striking for group theories, I guess, is that they exist at all, that they are infinite and not cyclic, that exist at all. And if they're non-amenable, I mean, of course, it makes me even more happy. But so this is quite monstrous. And another type of monster is the free Burnside group, where once again, by its very definition, it will not have a free subgroup. And once again, what is really striking is that this group exists at all, that they are infinite at all. And not only they're infinite, but if the proof of the fact that they're infinite is done sufficiently carefully by counting that there are infinitely many non-trivial words, but in fact there are so many non-trivial words that the growth contradicts the Grigor-Schuch criterion for amenability, then you have again paradoxical groups without the free subgroups. And so this
you could replace P by 101.
Oh, excellent. Thank you. Can I replace it by 5?
Explain it by adjunct and
I like your statements that is as claimed by X and the Y trusted, because I've been trying to find precise references for the dates, and one of my PhD students told me that in fact in 1978 it was reported by Neumann that Rips had stated something that was trusted by Schuch. So now you tell me that someone trusted 5. Okay. 101. Okay. Very nice. In any case, I'd like to have other examples, and so I'd like to have examples that you can really hold in your hands, even if you don't deal with numbers as large as 101 or 10 to the 75. Right. And so I'd like to give more answers, and in particular, if these things are monsters, I'd like to find maybe smaller monsters or more friendly monsters or less monstrous monsters, so pet monsters. And that's what I'd like to do now if I have some time left. I can speak until 11, is that so?
Yes.
11, okay, thank you. So let's try to do that. So here is a beauty. And why do I say a beauty? Because I think the story of Frankenstein is such that Frankenstein decided to create a perfect human being. And the way to do that, or superior human being, the way to do that was to go get bits and pieces of nice specimens of human beings. And so you take a very nice leg of somebody who has very nice legs together with the nice face of, or at least a part of the nice face of someone who has a nice face, and put it all together. And then when Frankenstein did that, he found that the result was actually quite monstrous, even though he had taken the pieces of the prime pieces, prime cuts of nice specimens. And that's exactly what we're going to do. So I'd like to follow exactly this recipe of taking nice pieces of nice groups and combine them in a way that will create a small monster. Okay, so here's how we do it. So the nice group that we start with is 2x2 matrices, or if you prefer, Möbius transformations of the line. So recall that a 2x2 matrix can be thought of as acting on the line by the ax plus b over cx plus d formula. I think I wrote this formula somewhere here. And I draw the line like this because if you do that, then sometimes you will have the accidents that you have a 0 on the denominator if you are not careful. I'll try to be more careful later and avoid having 0 on the denominator. But if you're not careful, you have to accept that infinity is also part of your line. So this is the projective line, and that's the group that I want to consider, the group of projective transformations of the line. So ax plus b over cx plus d. So these are 2x2 matrices. The center acts trivially, so in fact it's PGL 2R. That's a very nice group that we know very well. It contains a lot of free subgroups, and all is well. All right, so that's, I think of them as continuous transformations of the projective line. Now, a typical such matrix, we know from linear algebra that it has 2 fixed points corresponding to the eigenvalues of the matrix. That gives you 2 fixed points on the line. I say a typical one because we also know that sometimes you have only one eigenvalue, and even sometimes you have no eigenvalue at all because we do all this over the real numbers, so rotation doesn't have an eigenvalue at all. Right? But typically, generically, you have 2 eigenvalues, and this gives you fixed points. Now, what do we do? What we do is we use these fixed points to cut out a piece. Okay, so like this. I cut the line into 2 halves, and on the top, I keep my nice, beautiful ax plus b over cx plus d transformation, and at the bottom I put the identity. Okay, so this is a well-defined continuous transformation. Since I've been cutting at fixed points, I have no problem whatsoever with the pasting. I reassemble my circle at the 2 points that are fixed anyway, so nothing happens. And I get a nice transformation of the line. And the group that I want to introduce to you, the group is the group of all these piecewise transformations of the real line. And I insist of the real line. That is, now I'm really careful not to move infinity, not to touch infinity. You can forget about infinity. There's no infinity. Okay? You take transformations of the real line that are obtained by taking a piece of a projective thing, so you don't touch infinity, and then I can glue anything else, so another piece, for instance, the identity, or so these are piecewise projective transformations. That forms a nice group. it's an uncountable group, but of course you can make it countable if you restrict your matrix to have coefficients, for instance, in the rational numbers or in some nice ring in a number field. All right, so that's the group that I want you to think about. And there are two theorems about this group. First of all, it's not amenable. And secondly, it doesn't contain a free subgroup. Okay, so this is an example of a monster. It's a non-amenable group without free subgroups. And I think I have enough time to prove both theorems if I speed up a little bit. So I want to prove to you that it's not amenable, and I want to prove to you that it doesn't contain a free subgroup. I just want to be sure that the definition of the group is clear. I give you an example of an element, a non-trivial example, right? And then it's a nice group. Transformation. I don't know. This exceeds my parsing capability. Yeah. Anyway, I'll prove it and then we see what is proved.
So the coefficients
so a priori they're real numbers. I'm going to give the proof that it's not amenable for coefficients in any ring that is dense in the real numbers. So if you want a countable group, you can take a ring like z square root of 2. But you cannot take a z. I'm going to use the fact that it's dense in R. Yeah. All right, so let's prove that it's not amenable. And to prove that it's not amenable, I will have to convince you that it's useful to look at means not just on groups or on spaces, but on equivalence relations. So what is a mean on an equivalence relation? So first of all, you start with a nice space. The space will be the line in our case, so it doesn't need to be too complicated. You can think of the space as the line. And you start with an equivalence relation on this space. So what is an example of an equivalence relation? Well, if you have a group acting on the line, then the orbits of the group, that's a nice equivalence relation. These are the relations that I want to think of. And in the back of my mind, I think of all this in the measurable world. So maybe X is just a measurable space, so Borel space. But in our case, it's the real line. All right. So a mean on a relation, by definition, this really is, okay, a mean on a relation means a mean on each orbit. That's a mean, okay? So you want to put a mean in the old sense as a set, a finitely additive probability measure on each orbit. There's a measurability condition. And the mean is called invariant if it depends only on the orbit, not on the points. Okay? All right, that's an invariant mean on a relation. And you call the relation amenable if it admits such a thing. All right? So it's actually simpler than the case of groups. It's even simpler. You forget the group structure, you just look at the orbit structure. You want a way to measure subsets of each orbit. And if this way to measure subsets of the orbits depends only on the orbit and not on the point, you call it invariant. So there's an obvious example of this. Namely, if I'm talking about a group action on a space, and the group is amenable, then the relation is amenable. Why? Well, take a mean on the group, and every orbit is by definition the image of the group under the action map. So you push forwards this measure on the group to the orbit, and that gives you your mean. Okay? And the fact that the mean was invariant on the group precisely tells you that it depends only on the orbit of the point, not on the actual point itself. So that's an obvious example, and it's almost the only example you need to know. So you start to wonder why I want to talk about relations rather than sticking with groups. Well, the reason is that it's simpler. It's just simpler to think of the orbit structure of a group rather than the actual algebraic multiplicative structure of the group itself. And here's a nice theorem that I will use. So if you take the projective group, or 2 by 2 matrices, and if you take a dense countable subgroup, then this example of an action is not amenable. So the orbits are not amenable. Okay, so that looks a bit like a mysterious theorem if I state it like that. And why is it so important that the group is dense? This becomes false if the group is not dense. But I'd like to try to convince you that it's not such a mystery. So in fact, this is a difficult theorem, but the reason it's difficult is completely extraneous to what I'm trying to present here. The reason it's difficult is that what they really prove, Carrière and Gis, is that such a group contains a dense free subgroup. Okay, that's the hard part. And then it is very straightforward, so it's really a few-line argument that if you have a subgroup that is actually free and dense, that the relation cannot be amenable. And I tell you how it goes. Suppose that you have a free group that is dense in a Lie group, Okay, it doesn't need to be SL2R, it can be any Lie group. Suppose you have a free group that is dense in a Lie group, then you take a nice paradoxical decomposition of the free group, which is the only one that we have seen with our eyes and felt with our hands. You take that, you transport it on every orbit, and the fact that it's dense allows you to use the density point arguments to see that, in fact, the relation also has to be paradoxical. Okay? So the theorem is hard because they wanted to have an abstract statement about dense subgroups, not about dense free subgroups. And actually, I have to say it was hard enough that they failed to generalize it to other Lie groups, and then this has taken quite a number of years to be generalized. And in the end, I think the best proof for general Lie groups has been given by Tariq Callender and Emmanuel Breuillard, who really proved that these dense subgroups have dense free subgroups. But we will not need any of these difficulties because we will only look at groups that will have by construction a dense free subgroup. So I will really use free groups, for instance, in SL2Q, or I guess you can take SL2 of some other ring in a number field. You can just write down free subgroups that are dense. Okay, so you don't need the hard part of this theorem. All right, so these are relations. And I want to draw a conclusion from that, namely that if you have such a group here, for instance, 2x2 matrices, the relation it produces on the projective line is not amenable. Okay. Because if it were, then you'd prove that the relation it produced already up here on the group would also be amenable, but it isn't. Okay, that's the conclusion. So here you have a source of non-amenable equivalence relations. Okay? And again, it's not really hard because you can start with a group that has an explicit free subgroup. So it's not hard. Okay. Now, we are close to the end of the proof of non-amenability of the group H, because at that point, you just need to show that from the viewpoint of the relation, this piecewise group is as good as a free group. Okay, so now we'll just show that the relation produced by this Frankenstein group has relations that are coming from a free group in 2x2 matrices. So here's how we do it. So I'm going to do everything over the rational numbers. That way I'm sure that it's countable, but you could do it over any ring that is a countable ring that is dense in the real numbers. And here's what we have to do. I draw a picture. So we want to prove that our group has exactly the same orbits as 2x2 matrices. Right? Then we're done, since 2x2 matrices contain free subgroups. So it's really a cheat. I'm using the free group to prove that this group is not amenable. Okay, so we actually do it now. We do it. I take a point, I take a group element G, and I have to show that I can obtain GP, so I can obtain the same action as my 2x2 matrix, as my free group of matrices, by using only elements of the group H that fix infinity. So how do I do that? I look where P goes, it goes to some points GP, and all I need to do is I need to bring it back to where it came from, to bring back infinity to where it came from without moving my point P again. Right? Because then I fix infinity. So I just have to prove you that I can fix infinity and get the same thing. Okay, so let's look at the fixed points of G. It has two fixed points, usually. If the fixed points are as shown, we're done. Why? Well, because remember that I can cut along the fixed points. And if I do the identity now if I do the identity below again, then I don't touch the image of my point. And I can bring back G infinity to infinity by just taking the inverse of G. Okay? So if the fixed points are like that, I'm done already. I've proved that piecewise is powerful, right? I can do what I want on different parts of the circle. So I'm done. The only risk is that maybe the combinatorial configuration of the fixed point is different. In that case, I have to work a bit harder, but there's a trick, which is that I just first do a huge translation, so translations don't move infinity. And if you compute the row transformation of your 2x2 matrix, you find that the fixed points, the eigenvalues, will actually converge to the points where I want them to be. So if the translation is large enough, I'm done again, I'm in the right configuration. I did a computation for you, just in case someone likes to do computation with 2x2 matrices. So here's the translation. This is translation by t. That's a 1 here. It looks like a 0, but it's a 1. And that's it. So that is the complete proof of non-amenability. And I think I even have a few minutes left to give you a complete proof that this group is free group free. Okay, but that's non-amenability QED. All right, so let's do the proof that there's no free subgroup, and this is my last slide. So the proof should hold here. So this proof, I should say, is not very original. It's lifted from similar proofs for piecewise affine maps, but we'll go through it together and have a complete proof. So the first thing to do is to observe that I'm going to use here some amenable aspects of the group H, namely that the stabilizers are metabelian, the stabilizers locally, the germs are stabilizers. Right? If you have a 2 by 2 matrix that fixes the point 0, then the stabilizer of 0 looks like that. That's metabelian. And any other stabilizer is conjugate to that. So I'm going to use that as metabelian. All right. So the statement we really prove is much stronger than just that you don't contain a free subgroup. We prove that if you take any two elements in the group, F and G, then either they generate something metabelian, so it can't be free, or they contain a copy of Z2. So again, it cannot be free. Okay, so this dichotomy excludes that F and G generate a free group. Let's prove it. All right, so F and G are given, and I can assume that there's some words W that's in the second commutator that is non-trivial. Otherwise, it would be metabelian, I'm done. All right, so I assume it's not metabelian. That means I can take a non-trivial words in the double commutant. And then I draw a line. So we're going to examine on this line the action of F, G, and W. All right, we're going to look at these three elements, the two generators F and G and W. All right, so first I look at the support, let's say the support of F and the support of G. So since it's piecewise, since this is a piecewise group, the supports are always intervals, so a finite number of intervals. To make the picture easier, I just draw one interval. But the argument is the same if you have 10 to the 75 intervals. Okay, so it's finitely many intervals, I draw one. That's the support of F union the support of G. Where is the support of W? Well, by definition, it's contained in there, right? Because if W is not trivial somewhere, then F and G have to be non-trivial. Okay, so the support is F or G have to be non-trivial. So the support is somewhere here. Now, here is the crucial point. The crucial point is that this inclusion is strict. I claim that the red line is strictly shorter than the green line. And why is that? Because imagine that you're at the end of the support, at the end of the green line. Okay? What does your group do in a neighborhood of this point? Well, it is metabelian, right? We just discussed this. In a neighborhood of the fixed point, it has to be metabelian. But W is in the second commutator group, so W has to be trivial there. Right? So this metabelian business tells us that in the neighborhoods of the endpoints, W is trivial. So the red line is really strictly shorter than the green line. That's all I need to know, because now I can choose a point there. Right? I can choose a point that's green but not red. And then I start to move it to the right. So since the point is not fixed, it's in the support of F or G, so it's not fixed, it means I can move it. Without less of generality, I move it to the right. And then I'm still not fixed, so I can keep moving it to the right since I'm not fixed, until ultimately I go further than the red line. I can do that, otherwise I would hit the fixed points. Okay? So I can move it all the way to the right. You see, I find an element H that moves it all the way to the right. Now, what does this tell me? It tells me that the support of W, the red part, has been moved entirely to the right of itself. Right? I've moved everything to the right, further than the red line. So the support of W and its image are disjoint. But the image is just the support of the conjugate. So I've found W and the conjugate that have disjoint supports, and that means they generate a copy of Z2. And I think it's 1100, so I put maybe a QED sign there. Thank you.
Thank you, Nicolas. Questions?
So is there a version of Thompson T group?
Yeah, maybe I just repeat your question because I have a microphone. So is there a version of Thompson's T group or Thompson's F group, maybe also? Well, yes, because Thompson's group F and T can be thought of as the piecewise projective transformation of the line with integer coefficients, right? So it seems to be very close to these groups here. As you saw in the proof of non-amenability, I used in a crucial way that my coefficients were dense in R. And so it means that what I said does not apply to Thompson's groups, but indeed they live in this family. So to be completely precise technically, there's a little distinction here. So I think it's Greenberg and Thurston who first noticed that Thompson groups have a realization as piecewise projective groups. But more precisely, it is piecewise projective with rational cut points. And as you know, eigenvalues are not rational but quadratic. They are quadratic thirds, right? But this is rational. And this makes a big difference because if you cut only at rational points, then since there are no units in Z, you find that in fact you're going to be C1 smooth. So you're going to have some kind of spline group. So it is not quite exactly then the group I defined because of where you cut. But I mean, I don't think this changed anything to the arguments. The point is the arguments breaks down completely when you have a discrete set of coefficients. Yeah.
And so is the T version C star simple?
The question is the T version C star simple? So I don't know, but I guess the motivation of your question is that the obvious argument against it doesn't work, since the obvious argument against it would be to find an amenable representation that would be, so the obvious argument doesn't work, and I don't know the answer. Yeah.
Because it would maybe give another proof.
Right. Yeah. So, yeah. I don't know the answer.
Do you know how many pieces you need for a paradoxical decomposition?
No. So the question is, do we know how many pieces we need for paradoxical decomposition? A Tarski number? No. And that's, you know, how do we know? I mean, not me, but the people who proved, you know, that you have lower bounds for and upper bounds for paradoxical decomposition. How do they know that? It's always by spectral estimates, right? So it's a miracle that they can have spectral estimates that are precise enough to say that to say that you have certain Tarski number appearing, right? But here I have nothing. However, I think one thing that could be tried is to take the paradoxical decomposition of the free group and try to carry it through this proof, through the relation, and get an estimate. So this definitely should be tried, yeah. I haven't.
Any further questions? Okay, let's thank Nicolas again.
Thank you.